Sir, good evening, sir. Kumaravel, sir.
Good evening, Prince. Good evening, all of you.
Good evening, sir.
Good evening, sir. Yes. Sir, please turn on your camera, sir. Kumaravel, sir, shall we start, sir? Your mic is muted, sir. Shall we start, sir?
Please start.
Okay, sir. Mithun?
Yes, sir.
You can introduce just.
Good evening, everyone. On behalf of Kamaraj College of Engineering and Technology, Department of EEE, I am honored to welcome you all to our faculty development program on the topic Navigating the Green Revolution, Integrating Electric Vehicles and Hydrogen Fuel Technologies for Sustainable Mobility. It's a pleasure to see so many dedicated educators gathered here today. First and foremost, I would like to extend a warm welcome to our esteemed guest speakers, facilitators, and participants. Your presence here is a testament to your commitment to excellence in teaching and learning. The objective of this program is to provide a platform for faculty members to enhance their teaching skills, share best practices, and stay updated on the latest trends. We have a packed schedule of engaging sessions and discussions that will help you refine your pedagogical skills and become more effective educators. Before we begin, I would like to take a moment to acknowledge the importance of faculty development in shaping the future of education. As, as educators, we play a vital role in inspiring, motivating, and guiding our students. Your dedication, expertise, and passion for teaching are essential in creating a supportive and inclusive learning environment. Once again, welcome to our faculty development program. I hope you find the sessions informative, engaging, and thought-provoking. Let us work together to enhance our teaching practices, share our experience, and learn from each other. Let's get started. As the world continues to transition towards a more sustainable and eco-friendly energy landscape, hydrogen fuel cells have emerged as a promising technology with a vast potential. With the ability to provide clean, efficient, and reliable energy, hydrogen fuel cells are being explored for a wide range of applications from transportation and stationary power to industrial process and energy storage. I'm happy to introduce our chief guest, Dr. S. Kumaravel, working as Associate Professor in Department of Electrical Engineering in National Institute of Technology, Calicut, Kerala since December 2008. He has acquired BE in EEE from Bharathasan University, Tripurapalli in year 2002 and completed his MTech in Power Systems from National Institute of Technology, Tiruchirappalli and PhD in Electrical Engineering from National Institute of Technology, Calicut, Kerala. Also, he has completed postdoctoral fellowship in the area of power converter applications in power systems from University College, Dublin, Ireland. His major areas of research are design and development of DC to DC converters, stability enhancement of microgrid, solid state transformers, etc. As on March 2024, he has published more than 45 research papers in SCI journals, including 18 IEEE transaction and 4 papers in IET Power Electronics and several papers in reputed IEEE international conferences held in India and abroad. He has supervised 11 PhDs and 56 MTech scholars. He has completed 4 sponsored research projects and has 2 ongoing projects with approximate cost of rupees 1 crore from CPRI and Spark. He has been cited in the list of top 2% researchers in the world of Stanford University. He has received awards such as Young Research Fellow from the Ministry of IT, Government of India. Young Scientist Award 2017 for Engineering Stream of KSESTE, Government of Kerala. Outstanding Branch Counselor Award 2018 from IEEE Kerala Section, IEEE PES Chapter Outstanding Engineer Award, etc. He is a senior member of IEEE, the member of ISTE, an institution of engineers. In addition to his research, Dr. Kumaravel has been a passionate educator, guiding faculty and students alike to explore new avenues of learning and innovation. Dr. Kumaravel's involvement in this program will surely provide us with a valuable insights and help us enhance our teaching methodologies and research skills. We are privileged to have him with us today. I am confident that his session will be both enriching and inspiring. Now I request our resource person to facilitate the gathering. Sir, please, sir.
Very good evening to all of you. I hope I am audible now. My voice is clear, right?
Sir, audible, sir.
Is it audible enough or?
Audible, sir. Any other participants, you can share your feedback. Audible, sir.
Okay. Audible, yeah. Okay. I have shared my screen. I think screen is also visible, right?
Yes, sir. Yes, sir. Visible, sir.
I'm moving the slide. Whether
The slides are changing.
Slides are moving, right?
Yeah.
Okay. So the given topic of my lecture is hydrogen fuel cell components and design. So thank you very much for providing the opportunity to deliver the lecture and also to share some of the expertise based on my experience I gathered in my lab. So I have almost planned the 3 parts of my lectures. The first part will be an introductory part. Second part will be focusing on a DC-DC converter for fuel cell applications. Third part will be the application of fuel cell based systems. These are the 3 parts I have planned. The given time is 1.5 hours. I will try my level best. For giving an introduction, the entire world is enjoying the life based on the advanced instruments, right from morning till going bed or during sleep also. Our life is highly sophisticated because of various machines, directly or indirectly. When these machines are operated, most of the machines are operated by electricity. Basically, they are consuming some energy. So, although there are different forms of energy, like thermal energy, atomic energy, hydraulic energy, solar energy, wind energy, etc., etc., most of the energy they are converted into electrical energy, that is so-called generation. After generation, we are converting into various forms. Usually it happens in load. So the one which generates electricity is called source. The one which consumes energy is called load. So electric circuit consists of the integration of a source and a load. So although there are different forms of energy, there are 2 states of energy. One is called a static form of energy and another one is a dynamic form of energy. So during energy conversion process, the static form of energy is converted into dynamic form of energy. For example, you take the energy stored in water reservoir using hydraulic turbines. we are converting the potential energy stored in water into a kinetic energy. So, during energy conversion, the static form is converted into dynamic form, but doesn't mean in energy, every energy conversion process it happens. For example, if we take a solar energy is already in the dynamic form. So dynamic energy is converted into another dynamic energy. Wind energy is another example. So we convert many forms of energy into electricity. So it is already proved that electricity is our fourth basic need of human. Apart from that, it has variety of advantages. So electricity can be transmitted over a long distance of time very quickly. Conversion efficiency is high, easy for control, account for tariff. Like that, there are variety of advantages in electricity compared to all other forms. Electricity is practiced for more than 150 years. Most of the energy is generated from fossil fuel, and recently, especially for the past 30 years, there are many issues we are facing due to fossil fuel, particularly global warming and the scarcity of fossil fuel. These are the two major issues the entire world is facing. One is global warming and air pollution. The second one is scarcity of fossil fuel. The scarcity of fossil fuel hit the economic security of a nation. You know, developing country like India, we import crude oil from foreign countries, which is one of the energy form. So when you are importing energies, so we lose our foreign exchange reserve. It means that the economic status of a country is decided by the amount of energy what we import. Government of India spent a major share to import energy from foreign country. So these are the two major impacts of the fossil fuel. So we are slowly moving to renewable energy sources. So coming to the history, this is the first electric station, first power plant in the world. So Prince, shall I switch off the video and shall I keep the mouse mic closer?
Sir, please, sir. Please, sir. You can, sir.
So this is the first power plant in the world, started by Thomas Alva Edison. This is the first power plant started in India. There are huge difference between these two power plants. The first one, started by Thomas Alva Edison, was a direct current. This power plant is alternating current. So one was AC, another was DC. The power plant started in India was in the year 1897. The first power plant was 1882. There was a current war happened in between. One side, Thomas Alva Edison, another side, Nikola Tesla. Edison stand with his DC, Tesla stand with his AC. So you know the major process in power system, generation of electricity, transmission of electricity, distribution of electricity, utilization. These are the four major sectors in a power system. If you see generation of huge amount of power in DC, there are a lot of limitations. You know, if you want to generate DC generators, if you go for DC generators, the main problem is commutation and insulation. So due to commutation, you cannot go ahead with massive capacity. That is one of the major drawback. The second one, if you go for insulation of a DC voltage, it is very difficult. So that is another challenge. So these are the two challenges they faced in the generation. Then coming to transmission, since we have a limited voltage in generation, we cannot enlarge the voltage, we cannot step up the voltage in the transmission. So that restricts long transmission of DC. But now we have HVDC after the development of power converters, particularly thyristors. HVDC system evolved. But Edison's time, there was no thyristor invented. So transmission of DC was a major problem at the time. Then coming to load, the one and only load was incandescent lamp when electricity was distributed by Thomas Alva Edison. Then later they gone to DC motors. In fact, DC motors particularly a very good advantage in the case of a utilization is concerned, a high efficient. But however, because of the drawbacks of or limitations in the generation and transmission, DC was not attracted in those times, which was completely ridden out by invention of Tesla on AC system. So the entire power system moved to AC at the end of the World War. You know, there are two types of AC, two types of electricity. One is AC and DC. Finally, the whole power system turned as AC. Generation was AC, transmission AC, distribution also AC. Utilization, you have induction motor, you have other type of loads, RLC loads. So that was the reason why Thomas Alva Edison lost his current war. It was won by Nikola Tesla in 1887. From 1887 onwards, most of the power system in the world was AC. Then slowly this electronic system started evolving, especially in the communication system. Later in the power system also, power electronics also slowly dominated. They started focusing on improving efficiency of electrical system, electrical loads using power electronics. For example, you take a incandescent lamp and LED lamp. LED lamp has higher efficiency than incandescent lamp. LED is a power electronics based load. Incandescent lamp is a conventional R load. If you take induction motor, for example, fan, we have today electronic regulator, power electronic regulator, which is having energy conservation. So now people are going for BLDC motor. Like that, most of the loads in industry as well as domestic turned as power electronic loads. So without power electronics, you cannot design any load today. That too smart loads. People are going to smart loads. That is one of the major share. Then coming to generation, especially in the past 30 years, solar PV and wind are the dominant distributed generators among any other generators. So power electronics, without power electronics, you cannot think about solar PV as well as wind energy. Then HVDC I already told, that is also power electronics. What finally I would like to conclude from this slide, entire power system is filled with power electronics. So without power electronics, you cannot run the show in power system today. Why? We want to improve efficiency, we want to improve reliability, we want to convert AC into DC. Suppose if you go for storage, the only storage possibility is DC today, like battery or any other source, ultra capacitor. So without power electronics you can't do anything. Now the attraction towards DC is also increasing year by year. However, Thomas Alva Edison lost his current war in 1882. If such power electronic system might have invented at the time, there is no doubt that he might have not lost the current war. All of you, I think, will agree with me, right? How many of you agree with me? Those who agree with me, just type Y in the chat box. Prince, whether they allowed to type in the chat box?
Yes, sir. Yes, sir. They can type. Sir.
Yeah. Yeah. Just yeah, I'm getting some response. Thank you. Yeah. The Thomas Alva Edison lost his current war because he faced problem in DC. But now that entire problem is ridden out by power electronics. He could not step up the voltage, step down the voltage, because AC can be step up and step down by a transformer. That's why AC succeeded. But now there are converters available to step up the voltage and to step down the voltage. The other problem, generation. Today solar PV is one of the predominant technology. You have the generation itself as a DC form. Now we are going to talk about solar PV. It is another fuel cell. It is another DC form. There are variety of generators available today in terms of DC form. So that is another important attraction of DC. Thank you for most of your responses. Finally, we are coming to the microgrid structure, that is a present maturity of power system. Power system in the small scale is already there in our home or in an industry. Variety of sources like solar PV, wind, battery of electric vehicle or our UPS. Most of the home people are using inverter. Like that, there are many types of energy sources arrived at the home or industry. Apart from that, we have utility. So microgrid is one of the matured technology today. Even people started operating. With this introduction, now we are moving to fuel cell. As I told, people are looking into new technology. Solar PV is such a one technology. Every home, most of the home particularly, they are electrified with solar PV. Among the participants, how many of you have already installed solar PV in your home? Just if you have installed solar PV in your home, just type PV in the chat box. Sir, I have PV of 5 kilowatt. You type 5 PV. If you have 1 kilowatt, 1 PV. Please type if you have already solar panel in your home, solar PV system in your home. Yeah, very good. I think Mr. Siddharthan, he typed he is having 3 kilowatt PV system in his home. Very good. I think our HOD, I think our maybe our Dr. Prince, he is having a 5 kilowatt solar PV in his home. Very good. Yeah. Thank you. I think another answer, Prakash, Mr. Prakash has typed 1 kilowatt. Very good. There are many people. I'm happy that among the participants, most of the people have installed solar PV in their home. If I ask another question, most of you will answer. Do you know what is that question? How many of you have inverter? Can you type with the battery capacity? Suppose if you have 100 Ah battery, can you type 100 battery, 100 B? Instead of battery, you type a word B, battery, B for battery. Yeah, very good. Prakash sir is typing that he has
150 Ah battery, very good. 150 Ah. And yeah, like this you can type the answer. I think most of you will answer. Very good. I am getting some more answers. 100 Ah battery. 150 Ah. Very good. Most of the people are having this 100 Ah, 150 Ah. Thank you. Oh, very many people. As I told, no, when you say solar PV, very few people have answered. But when you say how many of you have battery, many of them started answer, right? Thank you. So already such generators, small storage reached in our home. Wind, the major problem is we should have a wind prone area. Okay, one of my scholar done a research how to develop a low power wind generating system, especially for domestic system. We have technology, but we are trying to develop a product still. But the problem is, especially country like India, there are limited wind prone areas. Unless otherwise, if the average wind is above 4 meter per second, you can it will be feasible to install wind. Otherwise, it is not affordable. So that is one of the major limitation. Coming to the other thing, we have other massive source is fuel cell. But fuel cell is concerned rather claiming as a generator, people are calling it as a storage. Okay, now let us see how fuel cell is growing up. That is another attraction. Let us see some important points about fuel cell. It is an electrochemical device like a battery, so where chemical reactions are taking place and it produces electricity. There is no combustion. The electricity is, although hydrogen is a fuel, hydrogen is a highly inflammable fuel, you know very well. Suppose if you have a natural gas, if you burn natural gas, you can see a flame, maybe in blue color, or if there are more carbon monoxide content, it will be an yellowish color, right? But if hydrogen burns, you will never find a flame. It, that's what it is, inflammable burn. Okay, even rather rather generating electricity from hydrogen, the another route is hydrogen as a fuel in a thermal IC engine. Even in the other route also people are searching. Another route also active research is going on. So in electricity, when you are using as a fuel in fuel cell, there is no combustion process. So it is a static device, no vibration, no noise, mechanical energy is not involved. The chemical energy is directly converted into electricity. It's a clean when hydrogen is used as a fuel, no pollution. It is high efficient. Even if you are using hydrogen as a fuel in an IC engine, they are telling that the overall efficiency could be 40 to 60% only. But if you use in electrical method as a fuel cell, the efficiency could be more than 80%. So electrical route is more in efficiency. So 2 to 3 times than burning as a fuel. That is another attraction of fuel cell. During the electricity generation, it can produce both heat as well as electricity. If you have any thermal application, the heat from fuel cell can be extracted and it can be used as a byproduct. So heat is a byproduct from fuel cell. So it also produces water. You know, hydrogen fuel cell is concerned, the byproduct is water, right? Even if you run over a period of time, it can provide a water. That is another advantage of fuel cell. So just let me go to the physics of fuel cell. Particularly, I am seeing a hydrogen fuel cell. Like a battery, it has anode, cathode, and a electrolyte. Same like the construction similar to a battery. It has anode and a cathode. One side particularly from anode side, we inject hydrogen. Cathode side, we inject high pressurized air. Need not be an oxygen. By default, oxygen present in the air. So we are injecting high pressurized oxygen. Two reactions are taking place. One is called anode reaction. Another one is called cathode reaction. You know, hydrogen will never available in environment as an atom. It always available as a molecule. One hydrogen atom attached with another hydrogen atom. It is the first element in our atomic table. Starts with hydrogen, which has one proton and one electron. It never available in environment as an atom. It only available as a molecule, hydrogen molecule, which has two hydrogen atoms as H2. When it enters into anode, each hydrogen loses an electron. So two electrons are extracted from the hydrogen atom. So two proton atoms of hydrogen and electrons. So then the proton alone goes through proton exchange membrane. You can see this hydrogen, two hydrogen goes through proton exchange membrane and it goes to cathode, whereas in cathode the hydrogen is entering. So in the cathode reaction, oxygen reacts with the proton of the hydrogen and this electron combines there and it makes water, H2O, as a byproduct. It is just a formation of a water. That's it. So hydrogen reacts with oxygen and produce electricity and hydrogen as two products. In fuel cell, our main product is electricity and the byproduct is hydrogen. This is a hydrogen fuel cell, chemical reaction in a hydrogen fuel cell. In order to balance the equation, they are writing like 2H2. The complete reaction is 2H2 is equal to 4H plus 4 electron. In the bottom, they have 2O2, or I think O2. It's O2 plus 4H plus 4 electron minus gives 2H2O. I think in the first equation I made a small typographical mistake. Extremely, I'm very sorry for that. It is 2H2. It is 2H2 gives 4 hydrogen plus 4 electrons. I think the picture, it is very clear, but in the equation I made a mistake. Sorry. You can correct it. So 4H2, 2H2 gives 4H plus 4 electron minus. The next equation, it is correct. Okay. So this is a cell technology. In order to make a fuel cell stack like a battery, they are arranging cells in series and parallel. Here I am showing a series combination. They are connecting number of cells in series and they are forming a stack. And they are forming a common chamber to supply hydrogen and oxygen. So coming to the major components of fuel cell, one is the fuel cell stack. The picture indicates how the stack is made. They have a proper mechanical arrangement for supplying hydrogen and oxygen. In between, they have electrodes and insulation coating to avoid short circuits. Then they have that proton exchange membrane. Proton exchange membrane is there. Then they have the electrodes. That's the way they also added a catalyst to increase the speed of reaction. This is one of the major component of fuel cell, that is fuel cell stack. The next major component is a fuel supply system. See, the amount of electricity produced by hydrogen depends upon the amount of hydrogen and oxygen supplied. It is in the function of partial pressure of hydrogen and the partial pressure of oxygen. Mathematically also it's expressed. Due to time constraints, I am not going in detail. So fuel supply system is one of the major components. So when the hydrogen is stored in a particular pressure, they are releasing using a regulator. You can see the pressure regulator. It is a closed loop system. Then this pressurized hydrogen is injected into the fuel cell stack. Then it is coming down. Then they have a recycling process also. If the hydrogen leaves the chamber without a reaction, you can extract that hydrogen and it is circulated back to improve the efficiency. So circulation of hydrogen, that is nothing but fuel supply system, is one of the major part of the fuel cell, because the electrical characteristics of the fuel cell depends upon the amount of hydrogen and oxygen supplied. So that should be a perfect system. Then you have a cooling system. I already told hydrogen producer, fuel cell produces heat also. In order to keep a temperature constant, we have a cooling system also. Then another important component is a power converter and a energy management system. Where I have produced electricity, shall I directly connect your load? Suppose, assume that I have a 12 volt fuel cell. I have a 12 volt motor. Assume that both are DC. Fuel cell is also a DC. My motor is also 12 volt DC. Shall I connect these two directly? How many of you recommend to connect directly? Sir, I have a 12 volt fuel cell, 12 volt motor. Shall I connect these two directly? If you could recommend to connect directly, just type Y in the chat box. Otherwise, N in the chat box. Suppose you say this, sir, no, sir, you cannot connect these two directly. So type N in the chat box. Otherwise, type Y in the chat box. Yes, sir, it is possible to connect both. What will be your answer? Yeah, Mr. Sumar is coming with the first answer, N. He is telling that no. Yeah, other people also answering. Mr. Siddharan. Yeah. Miss Mercy. Dr. Vasanthi. Yeah. But nobody is telling yes. I think Dr. K. Morrison is also answering. Most of the people are answering no. That is correct. Yeah, why? Because the characteristics of a fuel cell is different. Characteristics of the motor is different. For example, you take the torque speed characteristics of a motor in terms of electrical is different. Also, the torque speed characteristics of speed, the voltage current characteristics of a fuel cell is different. If you directly connect these two, there are many problems we will face. One is the voltage level need not match. Voltage of fuel cell is different. I'm telling you nominal value only. I told you 12 volt. What is the guarantee that a 12 volt fuel cell always produces 12 volt, right? It cannot produce always 12 volt. Always there will be a variation, right? Because it has some internal resistance. So the amount of current delivered by the battery decides the effective amount of current. You know, for example, you take a fuel cell. Let me draw it here. Suppose you draw the internal resistance of the fuel cell, and this is a fuel cell, and this is the output voltage. The voltage across the fuel cell, let me call it as a load voltage, is equal to, if you write a Kirchhoff voltage law, VL is equal to the no load voltage of the fuel cell minus the current. Let me take this current is I, this resistance is R, minus I into R. This current is a load current. If more current, more drop. So if you draw these as a characteristics, this is your load current and this is your voltage across a load. So ideally speaking, it is a straight line. Ideally speaking, if internal resistance is 0, then VL is equal to VFC. No load voltage is equal to load voltage, ideally speaking. But practically speaking, it will come down, right? Because of the resistance. So this voltage drop increases when current increases. So due to this reason, we cannot connect it directly. If current is more, drop will be more. So if you are not providing a load with the recommended voltage or the rated voltage, it will not produce a rated power. If it is not producing a rated power, it cannot produce a rated efficiency. So it is not recommended to connect a fuel cell directly to a load. So we need a power converter. We need a power converter. Although both of them are DC, it is not recommended to connect directly. Then I told a thermal management system and a cooling system. There is another important component of a fuel cell. Then important one is safety. I already told hydrogen is involving in fuel cell. So there is a problem of safety. Unlike solar PV or wind, fuel cell cannot be handled as easiest compared to these two. Why? Hydrogen is a inflammable gas. Okay, so safety is a major concern. So you should follow all the safety protocols if you are installing a solar fuel cell. Solar PV is concerned, people are installing in the rooftop. There is no much environmental problem. There is no safety issue, much safety issue. But fuel cell is such a dangerous thing. You should have fire and safety rules, all these things to be followed. I'm coming to the characteristics of a fuel cell. So load current increases, voltage is coming down. You can notice down here about a 500 watt. Okay. So for example, you are operating here, you are operating in this region, or maybe operating in this region. Let me operate in this region. You can see approximately the current is 10 ampere and the voltage is 30. Let me operate here, then only it will be good. For example, assume that I am operating in 20 and 30. For example, ideally I am taking these two value. So 20 into 30 will be 600 watt, right? So 600 watt power I am getting. But when you take 600 watt power, the magnitude of current is 20 ampere. The magnitude of current is 20 ampere. The magnitude of voltage is 30 ampere. If you see the magnitude of current and the magnitude of voltage, there is no much deviation, right? Both are almost equal. Suppose if I take same 600 watt system, 600 watt load at a 200 volt system. Okay, suppose I have 200 volt system on the same power, 600 watt I am taking. Instead of 30 volt system, this is not ampere, sorry. Instead of 30 volt system, I am taking 200 volt system. So what will be the current? So the value of current is equal to 600 by 2, 600 by 200, right? So it will be 3 ampere. You can compare the magnitude of the voltage and magnitude of the current. So what is advantage of high voltage, low current? Because I squared R loss. You know what is I squared R loss, which is one of the major power dissipation in our electrical system. Usually this resistance are called as internal resistance of a source or a transmission system or anything. We are trying to minimize this R component. Although we are trying to minimize, you cannot minimize beyond a particular value. Already you are using a copper wire or aluminum wire. Reducing the resistance beyond a particular value is very difficult. Even you can go for gold also. Gold is one of the good material, no, conductivity material. If you go for a gold, resistance will come down. But what is the problem? Cost will increase. So Indian system, we are trying to minimize the cost. So what is the limitation? You cannot reduce the value of R beyond a particular value. You cannot reduce R beyond a particular value. So although you have a high current system in fuel cell, the I squared R loss is more. Suppose if you have 20 ampere at 1 ohm resistance, let me take. So 20 square times 1 is how much? 400 watt. right? Suppose if you have a 600 watt power produced by a fuel cell, assume that the entire internal resistance is 1 ohm. This 1 ohm will dissipate 400 watt power. Can you imagine then? Hello?
Your voice is not clear, sir.
Yeah, just a minute, sir. Just a minute. Yeah, sorry for the disturbance. What I would like to say, if you have 1 ohm resistor, it will dissipate 400 watt power. So feasibly, I am calling it as 0.1 ohm resistor. If you have even 0.1 ohm resistor, assume that you are increasing conductivity, so resistance is coming down to 0.1, even it can dissipate a 40 watt power. So 40 watt power in a 600 watt system, you can calculate the efficiency easily, right? So assume that 600 watt, 600 minus 400 is 40 is 560. So 560 by 600. You can calculate the efficiency easily. Even if you have 0.1, so it will become 560 by 600. The efficiency will be only 93%. Okay. Going the reduction of resistance below 0.1 is real task. Right? It is not possible to reduce the resistance below 0.1, right? It is tougher and tougher, right? Even reduction from 1 to 0.1 or even 0.1 to 0.05 is feasible. But going down further is really a very big challenge. So you have to think about a material based research. So what I would like to conclude here, compared to solar cell, fuel cell's major drawback is its high current density compared to the level of voltage. So the level of voltage is higher sometime than the current. That is one of the major drawback and limitation of fuel cell. Now I told the whole block diagram of the fuel cell looks like this. There is a fuel cell and there is a DC-DC converter. The purpose of the DC-DC converter is to enhance the level of voltage. So I told if you go for a 230 volt load, yeah. So if you go for this such a fuel cell, so for example, you have a load. Say I assume that I am going for a 230 volt DC, sorry, 230 volt AC. Fundamental, let me call it as a fundamental voltage, 230 volt AC. If you have 230 volt AC, you know the maximum voltage is 230 into square root 2 is a peak value. Suppose 230 into square root 2, it is equal to 325 volt. This is your 325 volt is a maximum value. If you want to provide 325 volt maximum value, maybe assume that I am operating at a modulation index of 0.8. So if you have 0.8, the required DC link voltage will be 400 volt approximately. So you should provide a DC voltage of 400 volt DC, 400 volt DC in the DC link. If you have 400 volt DC, fuel cell I told the maximum available is something like a 40 volt. Okay. So can you tell me what type of converter you use from 40 volt to 400 volt? So in the DC-DC converter receives 40 volt as input and I should produce 400 volt as an output. Can you tell me what type of converter is recommended? Can you please answer? Let me give the option like a boost, buck boost. 3 options I have given. I think Dr. K. Morrison, he has answered as a boost converter. Okay. The fourth option is modified boost converter. Okay. So 4 options I have given: boost, buck boost, modified boost. What option is recommended here? You please keep it in your mind. I have 40 volt as my input, 400 volt as my output. This is my research. Almost more than 10 years I spend my time with my scholars, particularly in this area on the high gain DC-DC converter. So first let me check, is it possible to produce a 40 volt to 400 volt from a 40 volt using a boost converter? You know what is the relation between a boost converter? V0 is equal to V in by 1 minus D. So if I put 400 here, this is my 400, right? This is my 400 and this is my 40 as my input voltage. Then what will be the value of D? Anyone? Ideally, the value of D is 90%. Ideally, the value of D is 90%. Duty ratio, D is a duty ratio. So duty ratio should be 90%. Can you please answer? Shall I operate the converter at 90% efficiency? If I operate at 90% efficiency, will I able to produce actually this 400 volt output? Maybe at 1 kilowatt power. This is a 5-mark question in BTech level, a boost converter. All of you remember the circuit diagram of a boost converter. It has one inductor, one capacitor, one switch and one diode. The switch is operated with the duty ratio D. In order to produce 400 volt from a 40 volt, I have to operate the converter at 90% duty ratio. At 90% duty ratio, you all may know the shape of the inductor voltage is like this. Turn on for 90% time, turn off for 10% time. This is the waveform. Now what will happen? What will happen? This is the shape of the inductor voltage over a period of time. And this is called one cycle, capital T. This is called one cycle, capital T. If you operate the converter like this, the problem is the inductor core will saturate. Inductor has to charge for 90, energize for 90% time, de-energize for 10% time. So what will happen? Definitely core will saturate. Okay. So designing a core at 90% efficient, 90% energization time is very big challenge. Okay. The first foremost problem. Second problem, every component has a parasitic value. Inductor has its own resistance, switch has its on-state resistance, diode has on-state resistance, capacitor has ESR, effective equivalent series resistance. So all these components limits the output voltage. Ideally, you may get 10 times the output input voltage. Ideally, 10 times the input voltage, but practically you cannot achieve. Practically, the boost converter is recommended to operate at 80% duty ratio. So at 80% if you operate, worst case scenario, it can produce only 5 times the input current. 5 times output input voltage. If you give 40 voltage, it can produce maximum 200 volt as output with the efficiency of hardly 80% at 1 kilowatt. Okay. Now what can you do? These are the limitations of boost converter. So what you should go? You should go for a modified boost converter. So in that area, we have very good publications. I have produced almost 7 PhD scholars, particularly in this area at NIT Calicut. So I will continue the topic later. The limitations of boost converter I will continue later. Before going to that, fuel cell is much convenient to call it as a storage device than the generator, because during peak power it can produce hydrogen as an electrolyzer, because every generator is a motor, every motor is a generator. So by reversing the process, however, I supply hydrogen one side, oxygen one side, it produces electricity. No, in the other way you do, one side supply water, other side you supply electricity. The reversible reaction will take place. I have shown a chemical equation. The chemical equation will be reversed, so it produces electricity. Sorry, it utilizes electricity and produces hydrogen, right? Let me go back to the previous slides. So this reaction will be reversed. So H2O turned as O2 plus 4H plus 4 electrons minus. In this way, the direction will be reversed. So it produces in this way. So it produces H2H2. Okay. So one side hydrogen will be released, other side oxygen will be released. So this is called electrolyzer. So in using electrolyzer, it can produce massive amount of hydrogen and you can store hydrogen. And in the other way, if you have electricity, produce it back. So hydrogen is fuel cell is one of a good storage device than call it as a generator alone. Okay. So before going to the topic, and any doubt from the audience?
No, sir.
So if you have any doubt, please ask me. So I already told one of the major limitation of boost converter is its voltage gain and its efficiency. Also, it has more voltage stress and high current stress. These are the drawbacks of conventional boost converter. Then you may ask a question, sir, if your voltage gain is limited, why don't you add two boost converter in series, right? So if you add two boost converter in series, what will happen? You will have two inductors, two capacitors, two diodes and two switches. If you have two switches, what is the problem? Sir, as you told, voltage gain is a problem. So instead of going for a voltage gain, what you can do? Add two boost converters in series, cascaded boost converters. So voltage gain is improved, no? So the gain equation will become 1 by 1 minus d whole square. 1 by 1 minus d whole square. At 80% duty ratio, it can produce 25 times input voltage, because 5 in each converter. So 5 into 5 can produce 25 times input voltage, right? If I give 40 voltage, it gives 25 times 40 voltage. How much? It can produce 1000 voltage. But I need only 400 volt, right? Then why don't you add two boost converters in series? Anyone, can you answer the question? Why don't we do that? Why we go for a high gain DC-DC converter? So why? That's what I told you. No, I have done my research especially for the past 10 years in this area. If you are able to add two boost converters in series, and I don't continue my research, no, what are the challenges? Why don't you have two boost converters in series? And why do you need a third converter, right? Simply solution is solved, no? Problem is solved. Your solution is obtained. Why don't you have two boost converters in series? Anyone? Okay. So if you have two boost converters in series, I told you there are two switches are coming in action. If you have two switches are coming in action, so two different control strategy, two different gate circuit, two different protection circuit, what happens? Cost increases. Okay, if you have more than one switch, you will have limitations in the control. Control complexity is high. Okay, that is one problem. The second problem, if you try to see two different boost converters, sorry, two different switches, you will have the impact on the transient. Switching always limited. Okay, so we are not recommending with the two switches, and moreover, one of the switch will have output voltage. The voltage stress will become output voltage. And there are many research works reported throughout the world to overcome the limitations of conventional boost converter, where our research highly focuses on reducing the number of components, increasing efficiency, reducing voltage stress and current stress, making source current continuous, should have a common ground. We should achieve the required output voltage in the region of 40% to 60% duty ratio. Like that, we have lot of advantages. With that research focus, we have carried out in the past 10 years. There are many high gain DC-DC converter topologies we have published. What you are seeing on the screen is one of the high gain DC-DC converter. You can see here, although the circuit has more number of capacitors, almost 4 capacitors it has, but it has only 2 inductors. If you see, the power density is limited when you have more inductors. But here I have 2 inductors, but I have 4 capacitors. So, although both are interactive elements, inductor is also reactive element, capacitor is also reactive element, it is recommended to minimize inductors. If you have more inductors, problems are more. So we are not recommended to have more inductors. Another one, you can see the entire circuit we have only one switch. I told if you have 2 boost converters in series, you will have 2 switches, but here we have only one switch. Like that, there are many advantages here. So this and all core mathematics, I am not going into this in detail. So analytical equations like mode 1 operation, mode 2 operation. We are assuming that the circuit operates in continuous conduction mode. The final output equation is 4 by 1 minus D, 4 times input voltage. Okay. Suppose you operate at D is equal to D at 80% duty ratio, it will produce 20 times input voltage. Okay. So there are many advantages in the circuit. I told the effect of parasitic element. Here you can see we are operating in the region of 40% to 60%. In this region we are operating. So you can see it has a limited effect on the parasitic. The effect of parasitic is more in this region. You can see here. In this region the effect is more, but here it is less. And if you see the duty ratio versus efficiency, it achieves almost 90% efficiency in this region. So we are recommended to operate in this region. Okay. A sample power rating I have provided. In those days, I think this is the work I have done during 2020. So So now we go with 100 kilohertz switching frequency. That time we designed with 20 kilohertz switching frequency, where the input voltage is taken as 24 volt, output voltage is taken as 350 volt. We have designed the inductance and capacitance properly. This is the experimental setup we had that time. The experimental waveforms also you can see. Performance comparison. So compared to all other converters, the number of components is 12. Although number of components are 12, we have only one switch. But number of diodes are 5. But the efficiency, the voltage gain is improved as 4 by 1 minus D. That is one of the major advantage. Like that we have done many work. This is another converter. I am not going to this in detail. So as I told, its thermal efficiency is improved. So now we started using silicon carbide switches. So with the help of silicon carbide switches, we have enhanced the efficiency to 90 plus. Almost in the experimental setup, some of the converters we achieved the efficiency of 96% even. We do really good quantum of work. You can see the efficiency is very high. And the main loss is switching loss. You can focus here. Losses in the switch is very high. Almost 47% loss is bared by diodes. Although there are 5 diodes, only 2 diodes are consuming more loss out of these 5. Okay. Although only one switch is there, that switch alone is contributing 41% loss. Whereas inductors and capacitors, the losses are less. Okay. So with this, I am coming to the end. I have shown one application as electric vehicle. And when you use it in electric vehicle, they are not using fuel cell alone. They are using a storage, a battery, lithium-ion battery or ultra capacitor. They are combining auxiliary storage. This is the main fuel cell. They have auxiliary storage. From this hybrid energy system, they recommend for electric vehicle. This is one of the application I am showing. So fuel cell cannot be recommended as an individual source, standalone source. It is also always recommended to club with storage. Okay, because it should provide a reliable electricity, ripple free electricity. Okay, because of increasing reliability and voltage ripple, they are going for adding storage devices. Okay, and also I told you one more the limitation. The amount of electricity produced by fuel cell depends upon the amount of hydrogen and oxygen supplied. Doesn't mean that if you supply more hydrogen, will it produce more electricity? Never. Because a chemical reaction takes place and it has its own delay, chemical time constant. But if you have demanding more electricity, what will happen? Your hybrid, your fuel cell cannot supply. So if you are not powering, instantly your load will not provide the expected response. So you have to provide the electricity quickly. So quick electricity can be produced by lithium-ion battery, because nowadays lithium-ion battery available with the capacity of 2C, 3C rating, right? 3C lithium-ion batteries are available. As quick as possible, it can provide electricity. So that is another important problem of a fuel cell. It's due to chemical constant. It cannot produce electricity quickly. Okay. So with this, let me come to the end. So the given time is 1.5 hours. So almost 1 hour 15 minutes over. So please permit me for a discussion. So please make it as more interactive session and let us have a fruitful discussion at least in another 15 minutes.
Questions? Participants, you can discuss with your sources.
Participants, if you have any doubt, kindly ask our resource person.
So if you are working in my area, please cite some of my papers. I hope there is no question. I found prints. I'm not finding any question. Yeah, I think there is a question asked by Mr. Shaktivel.
From Sakti, sir.
Shall we use wide band gap devices? Yes. In fact, one of the limitation of silicon carbide or silicon, conventional silicon based MOSFET or IGBT is its limited switching time. If you take a 600 volt 20 ampere MOSFET of silicon and a silicon carbide, usually the turn on time and turn off time of a silicon switch is approximately 200 nanoseconds. Okay. If you come to silicon carbide device, its switching time is altogether hardly 30 to 40 nanoseconds. Okay. So almost 10 times it is faster than silicon. So silicon carbide is high switching speed. So instead of operating, silicon is recommended till 20 kilohertz switching frequency. 20 kilohertz, sometime nowadays IGBTs are available with 30 kilohertz. Above to that, if you increase the frequency, switching loss will increase. So device will, threshold will be developed, not threshold, hotspot will be developed on the device and device will damage. So it is not recommended to increase the frequency if you go for silicon. But if you go for silicon carbide, even in my lab, we go ahead with 100 kilohertz. The main advantage of increasing switching frequency, the size of inductors and capacitors will come down. When you are bringing down the inductor size and capacitor size, the parasitic element, parasitic resistance offered by inductor and capacitor will come down. For example, rather having 5 millihenry inductance, you can bring down to 1 millihenry inductance. If you physically wind up a 5 millihenry inductance, assume that it is producing 100 millihenry, 100 milliohm. Now, if you go to 1 millihenry inductor, the resistance also comes down 5 times. So instead of having 100 milliohm, you can have 20 milliohm. So rather having 100 milliohm into that current square, you can bring down the efficiency higher. So one aspect, power density also increases. It will become more compact, small in size. Another one, efficiency also increases. That is one of the major advantage of going to wide band gap devices. Now people are practicing power electronic system with 100 kilohertz. Even product also available with 100 kilohertz. I hope in future, with the help of a gallium nitride GaN devices, the efficiency will go further above. Switching frequency also they are telling that likely can be improved to 500 kilohertz. Okay, I think 220 years back, operating a power electronic system with 5 kilohertz itself is a big achievement. But today, 100 kilohertz people are doing. Now people are predicting that in another 10 years, you can go ahead to 500 kilohertz. That is a major advantage of using a wide band gap devices like silicon carbide and gallium nitride. I think I have answered your question, sir. Thank you.
Thank you, sir. Sir, shall I conclude?
Yes, sir. Yes, we
Yeah,
can.
if there is no other question, please go for the conclusion.
We can do.
As the hydrogen fuel cell components and design is valuable for educators as it bridges theoretical concepts with practical applications in renewable energy, enabling them to update curricula and inspire innovation among students. It helps educators teach the multidisciplinary nature of fuel cells, covering material science, chemical engineering, and system design while promoting sustainable energy practices. By integrating case studies and hands-on projects, educators can enhance experiential learning, prepare students for careers in the growing hydrogen economy, and encourage research in the cutting-edge technologies. This knowledge also equips educators to address global energy challenges and foster a deep understanding of clean energy solution. Now, I extend my heartfelt gratitude for the successful completion of this session in this faculty development program. A special thanks to our distinguished speaker for sharing his invaluable knowledge and insights, enriching our learning experience. Thank you, sir.
Yeah, thank you very much for the opportunity provided. So have a nice day. We will meet in some other occasion. Thank you, all of you.
Thank you, sir. Thank you, Kumaravel, sir.
I request all faculty members to stay tuned for the next session. It will be started shortly.